This question says, an analytical chemist is titrating 177.8 milliliters of a 0.26 molar solution of aniline with a 0.72 molar solution of HNO3. The pKb of aniline is 9.37, and then it wants us to calculate the pH of the solution after the chemist has added 49 milliliters of HNO3 solution to it. So this is similar to the previous problem on the playlist. However, in this case, we do have a weak base being titrated with a strong acid. And in the previous case, we had a strong acid, or the opposite. We had a weak acid and a strong base. So let's again start by writing the reaction. In this case, we have C6H5NH2 aqueous, and we add to it nitric acid, HNO3 aqueous, and this donates a proton to this, so we get C6H5NH3, so it goes from 2 to 3, and it also has a plus charge, aqueous, plus NO3 minus, aqueous, so this loses an H and a plus, so it goes from neutral to minus. So this is basically what we have. And what we can think about is an ice table where we have initial, change, and equilibrium, if you will, concentrations of these different things. The problem is we are given concentrations, however, we're given them in the original solution, not in the final solution, where we added 178 milliliters and 49 milliliters. So to find the concentrations of these things, the concentration of, say, C6, H5 and H2, we need to use C1V1 equals C2V2, where the initial concentration is 0.2600 molar, and we added, if you can see up here, 177.8 milliliters of that, equals C2, the variable, times the total volume, which is the 177.8 plus the 49, which is a total of 226.8 milliliters. When you do the math, you find that C2 equals 0.203827 molar, and that's the sig fig. Now, we want to find the concentration of HNO3. And to do that, we use the same C1V1 equals C2V2, except the initial concentration of HNO3 is 0.72 molar, so 0.7200, molar. The initial volume of it is 49.0 milliliters. The new concentration, C2, is still the variable, and the total volume is still the same at 226.8 milliliters. When we do that math, we find that the concentration of the HNO3 is 0.15556 molar. So now we have the two initial concentrations of these things. This one is 0.203872 molar. This one is 0.15556 molar, and the initial concentration of this, when we first mix them together, is 0. Well, in this case, we have more base than we do acid. Note that the other case is possible, and if you have a case where you actually have more acid than you have base, please refer to the previous video where we talk about how to calculate the pH of the solution in that particular case. But for here, I'm just going to calculate it for this one, for this video, because in the previous video I did one where we had more of the strong, in the other case, base, and less of the weak acid. Alright, so in this case, we're going to react all of the HNO3. So we're going to do the change is going to be 0.15556 molar. When we react all of this, we're going to lose 0.15556 0.156 molar when we react all of this, and here we're going to gain 0.15556 molar. So basically we react all of this, so the equilibrium, or the final concentration of HNO3 is essentially 0. Now we subtract this out and we get 0.04827. That's the sig fig, and here we just get the 0.15556 molar because we were adding it to 0. Now, these are not truly equilibrium concentrations. We are making an assumption here that essentially any more that this acts as a base, if this further acts as a base, it's essentially negligible. Said another way, we allow x to equal 0 if we were to use the Ka or the Kb expression. And that may be an oversimplification. However, that is the simplification that we're using in this problem. And if we use that simplification, which happens to work in this example and worked in all the other examples that I checked, we can use the Henderson-Hasselbalch equation to solve this. And the Henderson-Hasselbalch equation is pH equals pKa plus log concentration of C5H5NH2 over concentration of that should be C6, C6H5NH3 plus. You'll notice we have the concentrations of the base and the conjugate acid, but we don't have is the pKa. But what we are given in the problem is the pKb. Well, if you recall, the pKa plus the pKb equals 14, or said another way, the pKa equals 14 minus the pKb. And I apologize that I'm all over the place, but with this camera I can't fit the entire sheet on one screen. So the pKa equals 14 minus the 9.37 given in the problem. That should be a minus, so it's 14 minus 9.37, and therefore the pKa equals 4.63. Now that I have the pKa of 4.63, I can go back to my Henderson-Hasselbalch equation. pH equals 4.63 plus log of the concentration of the acid, which is, of the base, which is 0.04827, divided by the concentration of the conjugate acid, which is 0.15556. We divide these and take the log, and we get that the pH equals 4.63 plus a negative 0.50831, where that's the sig fig. When we add these together, we get that the pH to 2 decimal places, because this is 2 decimal places, is 4.12. So this is very similar to the previous problem, except for the fact that we have a weak base and a strong acid. The important thing to remember here is the Henderson-Hasselbalch equation would not always work for these types of problems. And in fact, if you took something like quantitative analysis, you might run into a problem where the Henderson-Hasselbalch will not work. But as far as I could tell in the ALEX program, the Henderson-Hasselbalch did work for all of the questions that I saw.